In 1996, the astronomical community found itself on the precipice of a groundbreaking new frontier. Alan Dressler, in collaboration with a committee of esteemed astronomers, put forth a revolutionary concept: a telescope designed not to observe the universe in visible light, as the Hubble telescope does, but in the infrared spectrum. This seemingly straightforward shift in focus would enable us to observe the cosmos in its history with greater depth and distance than ever before. It was a daring proposition that would challenge the limits of technology, knowledge, and our understanding of the universe. At the core of this concept was the capacity to discern through the opacity of cosmic dust and gas clouds. For decades, astronomers had been constrained by these obscuring veils, which impeded their ability to observe stars, galaxies, and other celestial phenomena. These impediments were not merely an inconvenience. They were impeding our ability to answer some of the most fundamental questions about the universe. What was the origin of the first galaxies? How do stars and planets form in the densest and most obscure regions of space? Perhaps most tantalizing of all is the prospect of observing the earliest light to emerge in the aftermath of the Big Bang. The committee put forth the proposition that by observing in the infrared wavelength, these enigmas could be elucidated. Infrared light has a longer wavelength than visible light, which enables it to penetrate through clouds of dust and gas. This implies that an infrared telescope could observe regions that had previously been inaccessible, including stellar nurseries, where stars are born, and distant galaxies whose light has been stretched into the infrared by the expansion of the universe. However, beyond the scientific considerations, the committee's proposal also represented an extraordinary engineering challenge: the construction of a telescope capable of detecting the faintest signals from the most distant regions of space, while situated at a considerable distance from Earth in a location that could not be readily accessed for maintenance, would necessitate a level of precision and expertise that had not been previously attained. The National Aeronautics and Space Administration, NASA, considered the proposal with the utmost seriousness. By 1997, studies had commenced to ascertain the viability of constructing such a telescope. A multidisciplinary team, comprising scientists and engineers from both the public and private sectors, was assembled to evaluate the technical and practical viability of the project. The findings were unequivocal. Not only was the feasibility of the project established, but the telescope would also represent the most powerful space telescope humanity had ever created. This marked the commencement of the lengthy and frequently arduous journey towards the eventual creation of the James Webb Space Telescope. The telescope, named in honor of former NASA Administrator James E. Webb, required more than 2 decades to design, construct, and test. The project encountered a multitude of challenges, with its considerable size being a significant obstacle. In order to achieve the objectives set forth by the committee, the telescope would require a primary mirror that was significantly larger than any previously constructed. Indeed, the dimensions of the mirror were so considerable that it could not be accommodated within a rocket in a single piece. The solution was to design a segmented mirror comprising 18 hexagonal segments, each of which was capable of functioning in perfect harmony to collect and focus light from distant objects. The segmented mirror had to meet specific criteria, including being lightweight, durable, and capable of withstanding the harsh conditions of space. The mirror segments were coated in a thin layer of gold, which is highly reflective in infrared light, thereby further enhancing the telescope's ability to capture the faint signals from the farthest reaches of the universe. However, the design of the mirror constituted merely the initial stage of the project. In addition, the telescope had to be maintained at an extremely low temperature in order to detect infrared light. Even the slightest amount of heat could overwhelm the delicate instruments on board, effectively blinding them to the faint signals they were meant to observe. To address this issue, engineers devised a sunshield of a size comparable to a tennis court. It was constructed from 5 ultra-thin layers of a specialized material designed to block heat from the sun, Earth, and the moon. It was imperative that the sunshield be unfurled with precision upon reaching the telescope's final destination, situated at a distance of 1 million miles from Earth, at a point designated as Lagrange Point 2, L2. This location, situated beyond the moon's orbit, was selected due to its capacity to maintain the telescope in a stable position with minimal fuel usage, while also ensuring its continuous shadowing from the sun. The deployment process, encompassing the unfolding of the sunshield and the alignment of the mirror segments, had to be executed with precision and accuracy. In the event of any technical difficulties, there would be no opportunity for astronaut intervention. By 2002, NASA had selected the teams responsible for the construction of the telescope's various components. The official commencement of construction occurred in 2004, and over the subsequent several years, the project was confronted with a multitude of setbacks and delays. Technical difficulties, financial limitations, and even natural disasters posed significant risks to the project's success. However, the teams demonstrated resilience and determination in overcoming these challenges. The stakes were too high and the potential rewards too great to allow for the possibility of abandonment. By 2012, the various components of the telescope were nearing completion, and the process of assembling and testing them began. Each part of the telescope was subjected to rigorous testing to ensure its ability to withstand the extreme temperatures and vibrations it would experience during launch and in space. The sunshield mirror segments and scientific instruments were required to function perfectly in concert, necessitating an unprecedented level of precision and coordination. In 2017, the telescope underwent a final series of tests at NASA's Johnson Space Center in Houston, Texas. These tests included subjecting the telescope to the conditions it would encounter in deep space, utilizing a state-of-the-art thermal vacuum chamber. Notwithstanding the obstacles presented by Hurricane Harvey, which caused extensive devastation in the Houston area, the testing program proceeded apace. By 2021, the telescope was finally ready for launch. The James Webb Space Telescope was launched on December 25, 2021, aboard an Ariane 5 rocket from the European spaceport in French Guiana. The moment was one of immense anticipation. The success of the mission was of paramount importance, as it would represent decades of work, billions of dollars, and the hopes of an entire scientific community. The launch was executed without incident, and over the subsequent 30-day period, the telescope commenced its trajectory to L2. Subsequently, the sunshield was deployed, the mirror segments were activated, and the telescope proceeded to assume its final configuration. With its instruments now fully operational, the James Webb Space Telescope is poised to embark on a mission that will revolutionize our understanding of the universe. Its infrared capabilities enable it to discern objects that are too faint or too distant for other telescopes to detect. This includes some of the earliest galaxies that formed just a few 100 million years after the Big Bang. By observing these ancient galaxies, the telescope will provide insights into how the universe evolved over billions of years. However, its mission does not end there. Additionally, the James Webb Space Telescope will investigate the formation of stars and planets with unparalleled precision. Stars are born in dense clouds of gas and dust, which are referred to as stellar nurseries. These regions are frequently opaque to visible light, rendering them challenging to observe with conventional telescopes. However, infrared light can penetrate these clouds, thereby enabling scientists to study the earliest stages of star formation. By observing these stellar nurseries, the telescope will facilitate our comprehension of the processes by which stars and planetary systems, including our own, are formed. In addition to its primary objective of studying stars and galaxies, the telescope will also be used to search for planets beyond our solar system. In the past 2 decades, astronomers have discovered thousands of exoplanets, or planets that orbit stars other than the Sun. A significant proportion of these planets are situated within the so-called habitable zone, where the prevailing conditions may be conducive to the existence of life. The James Webb Space Telescope will be capable of conducting detailed atmospheric studies of these planets, searching for indications of the presence of water, oxygen, and other molecules that could be indicative of the existence of life. Furthermore, the telescope will facilitate the study of black holes, the most enigmatic objects in the universe. Black holes are regions of space where gravity is so strong that not even light can escape. They are often found at the centers of galaxies, where they can grow to enormous sizes by consuming stars and gas. The James Webb Space Telescope will provide new insights into the formation, growth, and interaction of black holes with their surroundings. Perhaps most exciting of all, the telescope may facilitate the resolution of one of the most significant questions in the scientific community. The question of whether we are alone in the universe remains one of the most profound and intriguing questions in the field of astronomy. By studying the atmospheres of distant planets and searching for the chemical signatures of life, the James Webb Space Telescope may provide the first evidence of extraterrestrial life. Even in the absence of definitive proof, the data collected by the telescope will contribute to our understanding of the conditions under which life might arise elsewhere in the universe. Ultimately, the James Webb Space Telescope represents the culmination of decades of work by thousands of scientists, engineers, and visionaries from around the globe. It is an exemplification of humanity's aspiration to investigate the unknown, to extend the limits of our knowledge, and to seek responses to the most profound questions regarding our position in the cosmos. The telescope's unparalleled capabilities will usher in a new era of discovery, one that will transform our understanding of the universe and our place within it. The James Webb Space Telescope is not merely a technological apparatus, it is, in fact, a time machine. This device enables us to gaze back billions of years into the past and bear witness to the genesis of stars, galaxies, and potentially even life itself. While its mission is still in its infancy, the insights it will yield in the forthcoming years will indubitably transform our comprehension of the cosmos and, in turn, facilitate a deeper appreciation for the marvels of the universe we inhabit.